Hey folks, this is section 5.4, working with integrals. We have three main topics to discuss in this section, using symmetry to simplify integrals, average value of a function, and the mean value theorem for integrals. Here's an example of an even function, or the graph of one, where it's basically a mirror image on the left and right hand side of the y-axis. This has a nice property that if you integrate from negative a to a, which means the negative some number to the same number positive, so negative 2 to 2, negative 5 to 5, etc., all your area is going to be doubled. Basically, it'll be this whole piece times 2. That's what this rule says. It says instead of integrating all the way from negative a to a, you can actually integrate from 0 to a and then multiply it by 2. See, they changed it here from 2 times the integral from 0 to a. So that'll be nice because then you only have to integrate half of it, and you can plug in 0 as one of your endpoints, which is usually pretty simple. So if you have an even function, you can exploit symmetry like this to make the problem a little bit easier. On the other hand, if you have an odd function, this is a double reflection. Picture this piece mirrored over here and then mirrored down here. That's what odd symmetry looks like. This has the property that this area is also the same as this area, except they are opposite signs. Remember, area up here is positive, area down here is negative. So if you integrate from negative a to a, again, it has to be a kind of a symmetric interval here, like negative 2 to 2. And you have an odd function, the positive area will cancel out the negative area, and the overall result will be 0. So that's nice. If you know you have an odd function from a boundary from like negative 5 to 5, automatically the integral, the area will be 0. That's what these two rules say, so let's try some examples. Here this problem is asking us to use symmetry to evaluate the integral, and the first thing to notice is that you don't have to. You could do it the long way and get the same answer, but it's a shortcut for a reason. It should save us some work. Also notice we're going from negative pi over 2 to pi over 2, so we do have like a negative a to a case. And the first thing I would do is factor out this 8. Because it's a constant, you can pull it out front and then focus on this piece. So we have the bounds that we want for one of these symmetry things, and sine x is an odd function. So we know that the integral of an odd function from negative a to a is going to be 0. So what we really have here is just 8 times 0, which is 0. And that is our answer because we know sine is an odd function, it's on that boundary, so 8 times that will just be 8 times 0. Here's another example we can solve using symmetry, but in this case we have two separate functions that have two different types of symmetry. First thing is, remember, you can split up an integral over addition or subtraction, so I split this into the integral of x to the 4th dx, and then minus 3 times the integral of x cubed. Now, this first piece is an even function because it has an even power. This piece is an odd function because it has an odd power. So we'll use the even symmetry here, break it up into the interval from 0 to 2 and multiply by 2. And this one will actually just be 0 because it's an odd function from negative 2 to 2, so that whole piece goes away. So here I did those steps. This first piece, we're going to go from 0 to 2 and then multiply by 2. That's our x to the 4th dx. The second piece, it becomes negative 3 times 0 because this is our odd function. So that whole piece goes away, becomes 0. And as you can see, we'll have 2 times the antiderivative of x to the 4th, which is x to the 5th over 5, evaluated from 0 to 2. And now, because we exploited symmetry, all we have to do is plug in 2. When we plug in 2, we get 32 fifths. And then minus, when you plug in 0, you would just get 0. So our final answer, if we multiply this together, we'll get 64 over 5. Next we have this formula for what's called the average value of a function, which is supposed to mean exactly what it sounds like. If you look at an interval from a to b, your function attains different heights. So like this one starts kind of high, decreases, starts to rise again at the end. There are an infinite number of different heights here if you pick an infinite number of x values between here. But if you think about an average says you add them all up and you divide by how many there are. In this case, adding them all up is kind of like finding the area under the curve. That's what this integral represents. And dividing by how many there are, since there's technically an infinite number here, we actually just look at the length of the interval. So b minus a would give us the length. So this formula for the average value is just says add them all up and divide by how many there are. If we try an example here, they want us to find the average value of this function, 3x squared minus 5x, over the given interval 0 to 2. So we'll set this formula up right here. The average value is equal to 1 over b minus a. This is a to b, so b minus a is 2 minus 0, times the integral from a to b, so the integral from 0 to 2, of our function f of x dx. So if we evaluate this antiderivative, first thing we're going to do is simplify the 1 over 2 minus 0 as just 1/2. Then the antiderivative here of 3x squared will become x cubed. Right, if you increase it by 3 and divide by 3, the 3's cancel. And then minus 5x squared over 2, evaluated from 0 to 2. So we have 1/2 times. When you plug in 2, you get 8 minus, and then 2 squared is 4, 4 over 2 is 2, so 2 times 5, that'll be minus 10. And then when you plug in 0, again in this case you get 0 minus 0, so that's 0. 8 minus 10 is negative 2, negative 2 times 1/2 is negative 1. So it looks like on this interval from 0 to 2, the average value of our function is negative 1. And if you graph it, you'll see that between 0 and 2, the 5x is actually bigger than the 3x squared, so you have some small negative values. If you think about the average height of that function, it should be roughly about negative 1. Lastly, we have the mean value theorem for integrals. To make some sense out of this, if you take a look at this piece over here and focus in on this side, 1 over b minus a times the integral from a to b, we could write the integral from a to b part as the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. That's what the fundamental theorem of calculus says to do for definite integrals. And then if we take that piece and multiply by the 1 over b minus a, we get this. And so they're basically saying this piece, which is this, equals f of c for some c between a and b, which is this. And now if you look at this piece here, it actually looks exactly like the mean value theorem that we learned before for derivatives. Right? This is kind of like the mean value theorem for derivative. This is the mean value theorem for integral. At heart, they say the same thing. If you take the average value of a function, then its derivative at some point will be equal to the average value. If you look at it in terms of the antiderivatives, now we have the antiderivative of f, but we're looking at the average value, will be equal to the derivative of that. Remember, little f is the derivative of f at some specific point. So really, this statement here is exactly the same as this one, except we're just calling this the antiderivative and this the derivative. And we're just rewording it in terms of integrals. Let's do an example using the mean value theorem. Here it says, find the points on the interval 0 to 1 for which this function equals its average value, which is basically a statement of the mean value theorem. It says find a value c where the function equals the average value. So the first thing we have to do is find what is the average value. So I ran through the steps here. This is a to b, so a is 0, b is 1. So we have the average value equals 1 over b minus a, the integral from a to b. And notice for this function, I distributed the 2x through. So you get 2x times 1 minus 2x times x, and you get 2x minus 2x squared. And we'll be integrating that from 0 to 1. So first of all, 1 over 1 is just 1, so we can drop that. The antiderivative here, using the power rule, will give us x squared minus x cubed, minus 2/3 x cubed. And then we'll evaluate that from 0 to 1, which is pretty easy because once you plug in 1, you just get 1 minus 2/3. And once you plug in 0, you just get 0, so you get 1/3 as the average value. So again, the mean value theorem for integrals says there will be at least one point on the interval a to b where your function equals its average value. So we're looking for at least one point on the interval 0 to 1 where our function, which again I have simplified here, multiplied out, will be equal to our average value, which is 1/3. So we just need to solve this equation for x. Since it's a quadratic, let's get everything on one side and let's write it as kind of our standard form of quadratics. I wrote the minus 2x squared first, the 2x, subtracted the 1/3 over. And I don't think this is going to factor, so we're going to use the quadratic formula. Let's go ahead and clean this up, just get rid of the 1/3. I'm going to multiply everything by a -3, also to make our first term positive, which you don't have to do, but it usually makes it easier. So this will become positive 6x, positive 6x squared, negative 6x, and this becomes a positive 1. Now if you run the quadratic formula on this, you should get two answers. X equals 0.211, x equals 0.789. Both of these values, they're rounded, so there's a little bit of error, but both of these solutions, if you want to get an exact value out of the quadratic formula, should make our function equal to 1/3. And as you can see, they're both numbers between 0 and 1. So when it says find the points, there could be one, there could be multiple. In this case, there were two. So these are our two answers. These are the two values that make our function equal to the average value.